what it is. Alright, let's take a look at question 8. In question 8, we're being assessed on how to generate or write polynomial functions from graphs using roots. Problem 8 reads, a polynomial function is graphed below. So we have the graph of a polynomial function right here, okay? The question is, which function could represent this graph? So we have 4 options. So now the question is, what is the connection? How can we connect this graph to the polynomial function or related polynomial equation? The connection is as follows. Let's note the following point. So one thing you want to note is that the x-intercepts, okay, the x-intercepts of the graph of a polynomial. What's the significance of the x-intercepts? Oh wait, they are the roots, also known as the solution, roots or solutions, or you can call them zeros too. Roots or solutions to the polynomial equation, to the polynomial function. Okay. Alright, so what does this mean? Well, that means that we just have to follow the following steps. We'll extract what the x-intercepts, roots or solutions are from this graph. We're going to set them equal to 0, multiply the resulting expressions by each other, and then we'll get what the polynomial function is. Okay? Alright, so let's do it. First one, we need to find the roots. What are the roots of this polynomial function? The roots are the x-intercepts, right? Let's see. So we have, this is the x-axis. So wherever the graph cuts the x-axis is the x-intercept. So we have an intercept here, an intercept here, and an intercept here. So this value is -2. This one is 1. And this guy right here is 2. So we have 3 roots or solutions or x-intercepts to this polynomial function. Alrighty, let's go ahead and write that down. So we have the roots are x equals -2, x equals 1, and x equals 2. Alright, next step, we're going to set the roots to 0. Set to 0. We are unsolving this equation, kind of, sort of. Alright, so how do we set them? How do we make them equal to 0? So I need this -2 on the left side. What do I combine with -2 so it becomes 0? Combine the opposite, right? The opposite of -2 is +2. So you add 2 to both sides of this equation. And what does that result? You end up with x plus 2, x plus 2 equals 0. Over here, I need this one to become 0. So what do you do to +1 to make it 0? You combine it with its opposite. The opposite of +1 is -1. So you subtract 1 from both sides. X minus 1 is 0. And then lastly here, what you do, you subtract. You do the opposite of +2, which is subtract 2 from both sides. Alright? Okay. So you do that, and then you end up with x minus 2 equals 0. Alright, so they've all been set to 0 now. Excellent. Now the next step is to multiply the left side, the resulting expressions on the left side. These are the factors, okay? So multiply the factors. So if we multiply the left side, this is the reversal of the zero product property, okay? So remember the zero product property, if you're working backwards, this is what you get. Okay, so set equal to 0. Now we're going to multiply. Now if you notice x plus 2 and x minus 2, there's something special about those two. Let's put them next to each other. So we have x plus 2 times x minus 2. Or let's do this. If you look at the options that we have, the component with 1 comes first. So let's put that first. Okay, so it's similar to what we have. So let's put x minus 1 first, and then x plus 2 times x minus 2. So that takes us to the question, when you are multiplying factors, does order matter? Yes or no? I'd like you to put your answer in the comment section below. Let's see if it matters or not. If you say it does matter, explain why. If it doesn't matter, explain why. If you say you can multiply in any order, then what property of equality are you referring to or provides you basis with doing that? The fact that we are reversing the order of factors being multiplied by each other here clearly shows that it's a legal process, but we want to know what you think. Okay, x plus 2 times x minus 2. That should help you remember a particular expansion of factorization formula. A plus b times a minus b is the factored form of a difference of squares. A square minus b square. So if you have x plus 2 times x minus 2, do you know what that's going to be? It's simply going to be x squared minus 4. Okay? So this is known as the difference of square formula. Now, let's assume you don't know this, okay? So we have to multiply these two because all the options involve some kind of x plus or minus 1 component and the product of the other two factors. So if you don't know this trick, it's okay. You just multiply it out. First, outer, inner, last. Bam. Just multiply it, right? Okay, so we'll bring down x minus 1. And if we multiply this out, we have x times x is x squared. X times minus 2 is minus 2x plus 2x plus 2 times minus 4 is minus 4 equals 0. And then we can simplify further. This would give us, what would that give us? It will give us x minus 1 times x squared. You notice that the middle terms can be combined. They're first degree terms here, like terms, but they're opposite, so they basically take each other out, right? And then we're left with x squared minus 4 equals 0. And we see where this plays a role, right? Alright, so this is the related polynomial equation. The function is f of x equals x minus 1 times x squared minus 4. The answer to problem 8 is option number 3. Alright? So this is the function that when graphed will generate this result right here. Okay? Another way you can do this problem is you just plug in these functions into the graphing calculator, and then you will see which one results in a graph that looks just like this. Alright, so let's take a look at how to do this using the graphing calculator. Of course, if you're doing it with a graphing calculator, you have to graph all 4 and see which one matches. We already know what the answer is, so I'll just show you how to graph the correct answer, and then you will see how it compares with the graph, okay? So f of x is your y. We're just going to enter the right side of the equation. So we have x minus 1 times quantity x squared, x raised to the second power minus 4. Hit enter, and then graph. Bam. So you see how graph number 3 matches perfectly with what we have on the left right here. Alright, so some of you might wonder, it's much easier or faster to use a calculator to determine if a function has a particular graph or not. So that takes us to the following question. If you can simply use a graphing calculator to establish what the look of a function is it necessary to be able to determine if a function has a particular graph algebraically or manually? Okay, so the question is, all this work we did right here to come up with the final answer, is that necessary with the availability of a calculator? Let us know what you think. Just post your answer in the comment section.